Hi, Physics 2, Mr. Janowski. This is Chapter 35, Homework 3, Problem 5. So we are analyzing this circuit. This is one of those things that, like I said, is like a Sudoku. Start with the clues you have, get some more clues, take the new clue with the old clue, and figure out the things. And you just keep going and going until you're done. It really reminds me a lot of Sudoku. I always have trouble with that word. Anyhow, so what are we doing? First, we want the equivalent resistance seen by the battery. So if we're looking at this, R1 and R2 are in parallel with each other, and that equivalent resistance is in series with the equivalent resistance of R3 and R4. All right, so let's see what's going on here. What that means is REQ. Let me write it out this way. 1 parallel 2, you don't have to write it like that, is going to be equal to 1 over 25, and I'm leaving off the ohms, plus 1 over 50, and I'm leaving off the ohms, to the minus 1. I'm just lazy. Leaving off the ohms is what's going on here. So take 1 divided by 25, plus 1 divided by, forgot the divided by 50, and I get 0.06, but of course I want the inverse of that. Don't forget to do that. So take that to the minus 1, and my calculator is saying 50 over 3. My calculator is trying to be helpful, but I would rather have the decimal. So it's 16.6 repeating. Let me call this 16.667. I'll do that, and now I will write the ohms. So that guy ends up being that. Now for these guys. All right. What's going on here? The equivalent resistance of 3 parallel with 4 is going to be equal to 1 over 50 plus 1 over 75, that thing taken to the minus 1. So ask calculator, 1 divided by 50 plus 1 divided by 75, hit enter, 0.03 repeating, take that to the negative 1, and you end up with 30. That's an easier number to write. So 30 ohms. So what does that mean? That means this circuit here is going to simplify to this circuit. I've got a battery. I've got this equivalent resistance, REQ 1 parallel 2, that's not even worth writing it all out, is 16.667 ohms, and that is in series with the other equivalent resistance, which is REQ 3 parallel with 4, that is 30 ohms. So that's that. And then from here, I want to go to, I guess I'll change colors for this. Now I have 2 equivalent resistances in series, so I just have to add them to get the final equivalent resistance of my last circuit here. So my last circuit here, there's my battery, and my 1 equivalent resistance at the end. Sorry, where was I? The battery's 18 volts. I didn't write that in the last one. It's okay. 18 volts. And this equivalent resistance is going to be 30 plus 16.667. So it's going to be 46.667 ohms. All right, that's my answer for part A. I'm keeping extra digits because I'm going to keep using this number and rounding and rounding. So here's my answer for A. That was easy. Now I want the current leaving the battery. So how can I get that? Well, that's going to be easy. That'll just be Veer. I'm going to write it up here to save a little bit of space. Okay, so V is equal to IR. Therefore, I is equal to V over R. V is 18 volts. And the R we're going to use is this equivalent resistance. 46. Doesn't look like a 4 enough to me. 46.6 repeating ohms. Okay, so what is 18 divided by 46.6666666? You end up with not a nice number. 0.3857. And what are the units? The units are going to be amps. This is a current, after all. So there we go. There's our answer for B. Our answer for C What color? I'll go back to blue. I don't like to use yellow. Yellow and white doesn't make much sense to me. Anyhow, for C, what do we want? We want the power used by the entire circuit. Well, that's easy. That's just PIV. So what is the I? Well, the I is the I we just found. So what we're really saying here, let me make it clear on this diagram, is you have 0.3857 amps leaving this battery, going through this equivalent resistance, 46.667, and then, of course, going back around the other way. So anyhow, this I is our answer for part B. 0.3857 amps. And the V is the voltage of the battery. 18 volts. So if we do that number times 18, we end up with 6.942857. So let's call it 6.943. And what units? It's power, so it will have units of watts. Okay, so there's our answer for C. So we've done the easy ones. Now the hard ones. We want to figure out the voltage drop across each resistor, the current going through each resistor, and the power used by each resistor. So I think the best way to do this, rather than have your work all over the place, is make a nice table of what's going on. So first we're going to have the R's. Next we want the V's. Next we want the I's. Like V is part D, I is part E. And then finally we want the P. Okay, well R, we know what the R's are. R1 is 25 ohms. R2 is 50 ohms. R3 is also 50 ohms. And R4 is 75 ohms. So the way this table works is we always know the R's. If I know any other piece of information in any of these lines, I can figure out the rest of them. It doesn't even matter which one. It'll usually be you know V or you know I is what's going to happen. So if I know V here, I can get I, and then I can get P, because Vir and I is equal to V over R, and P is equal to IV. So this is going to be easy to do. Just remember, you always know R, and if you know either V or I, you can get the other one. And once you know I and V, you can get P. So it's easy. So how are we going to figure out any of these things? How are we going to get I or V for either one of these? All right. Well, we know that the current leaving the battery is 0.3857 amps. So we have that from this one. So this is why it's so useful to have your intermediate drawings. We also know that that's the current going through this equivalent resistance. So what does that mean? That means the voltage across 1 in parallel with 2, well, that's just going to be this I. Let me try to write it out here. I'm not going to have room. I'll write it underneath. We want this voltage, VI in parallel with, V1 in parallel with 2. Okay, well, V1 in parallel with 2 is going to be IREQ 1 in parallel with 2. So that's going to be, I'll write it here. The I we just decided, I've got 0.3857 amps going there. REQ, 1 in parallel with 2, is 16.667 ohms. So let's see what that gets us. 0.3857 times 16.667. And I end up with a voltage of 6.4284. So call it 6.428. That'll be enough volts. So what does that mean? That means that's the voltage across these guys. So that means that's the voltage across these guys. So from here to here, we have a voltage drop of 6.428 volts. Okay. So that means I now know the voltage across 1 and 2. 6.428 volts. 6.428 volts. Now, how do I get the voltage across these guys? Well, there's two different ways. One is I can just do the exact same thing again. If I want to get the voltage across 3 in parallel with 4, I'll do it this way first. Voltage of 3 in parallel with 4 is going to be the I. Again, it's the same I, 0.3857 amps, times REQ of 3 in parallel with 4. So 0.3857 amps times that voltage equivalent. I'm sorry, that equivalent resistance was 30 ohms. So take 0.3857 times 30, and you end up with 11.571 volts. So what does that mean? That means the voltage drop from here down to here is 11.571 volts. 11.571 volts and 11.571 volts. Okay. Is there another way that I could have gotten this number without using Veer? There is. If you look here at this middle circuit, let me put some of these numbers back in. So this was 18 volts being provided by the battery. The voltage across 1 in parallel with 2, we figured that that was 6.428 volts. Well, there's a rule, a law. It's called both. I call it Kirchhoff's voltage law that we're going to get to eventually. But basically, if you have 18 volts being provided by the battery and you've got a voltage drop of 6.428 volts here, well, the rest of the voltage drop has to be across here. So we could have just gotten this one just by saying V of 3 in parallel with 4. Well, that has to be voltage of the battery minus the voltage of 1 in parallel with 2. So 18 volts minus 6.428 volts. And if you do that, I can already see that the rounding has worked a little bit differently. 6.428. We would have gotten 11.572 volts. This answer is the same as this answer, minus the rounding. So that would be another way to do it. You don't always have to do it, the same way. There's often other shortcuts you can take. This way, frankly, would have been maybe a little bit easier. Anyhow, from here, what do you do? I don't think I'm actually going to, what the hell, I'm here, I'll do the whole thing. If you know what to do from here, maybe you could stop watching the video. We want to get the eyes. Oh, I need more room. I should have drawn this a little bit bigger. To fill this out, we want the eyes. Remember, I is equal to, not 4, I is equal to V over R. So we want those, and we want the P's. And remember, P is equal to IV. Okay, well, to get the I's, I can just take this voltage, 6.428, divided by 25. And I will end up with 0.25712. I'll just run it off there. Amps. To get the other one, it's going to be 6.428 divided by 50. And I end up with 0.12856. So I'll round it up to 6 amps. Okay. So I just did I is equal to V over R. I mean, you can do it that way. Perhaps you can also see that these two currents here, so that's the current. Let me change colors. This is all getting very busy. The current I1 plus the current I2, well, those two currents have to be equal to the current that was leaving the battery, which was 0.3857. Okay, so after you figured out what this one was equal to, you could have gotten the other one just by subtraction. That would have worked too. I don't know. Do it whichever way you want. If you're already in a groove of doing I is equal to V over R, just do it that way. So we'll finish. And I realize I should finish this video because there are things I want to point out at the end. To get I3, okay, well, that's going to be V3, 11.571, divided by R3, which is 50. So that's going to give me 0.23142, so I'll just call it 4. Again, I could get the other one by subtraction, but we'll do V over R again, which was 11.571 divided by R4 is 75, and I end up with 0.15428, call it 3 amps. So once again, if I take these two numbers and add them together, I should get this number. And I do. I'm happy. And then finally, P. Well, this is just PIV. So take your I, multiply it by your V. So 0.2571 times 6.428. And you end up with 1.653, and it's going to be watts because it's a power. Okay, for P2, well, that's going to be I2, 0.1286 times 6.428. And I've got 0.8266 watts. P3 is going to be I3 times V3. So 0.2314 times 11.571. And I get 2.6775, so rounded up to 8 watts. And then the last one, P4. Well, that's going to be I4, 0.1543 times 11.571. And I end up with 1.7854. So 85 watts. Okay, now there is a relationship between all of these powers as well. If I take P1 plus P2 plus P3 plus P4, so I'm going to take all of these numbers, add them all together, and what number do I expect to get there? 1.653 plus 0.8266 plus 2.678 plus 1.785. If I add them all together, I end up with 6.9426, call it a 3, watts. So where have I seen this number before? This is the total amount of power being used by all of the resistors in this circuit. Well, that number there has to be equal to this number here. This is the power being provided by the battery. So the battery is providing this power. The resistors are using it. They're dissipating it. They're wasting it. They're using it. There's different ways of saying it. So that's how that works. So yeah, look at this. There's lots of small math on this page. It can seem a little tedious. The keys are make the intermediate circuits. So if you remember at the beginning, we started here with the big circuit here. We found an equivalent resistance for this guy. We found an equivalent resistance for this guy. We drew an intermediate circuit. We found the equivalent resistance of these guys, and we drew this one. That got us down to part C. That was enough to get us A, B, and C. And then from there, you kind of work backwards. From your last circuit to the one in the middle, to maybe there'll be another one in the middle, to maybe there'll be another one in the middle, and then finally all the way back to the original one. So this is why it's important to make the intermediate circuits. So, yeah. I actually find these problems kind of fun, as long and tedious as they are. It's the same kick I get out of doing Sudoku or doing a crossword puzzle. You get a little bit of a clue in this one, and that gives you more information to do another one. So it's good. Anyhow, I have no idea how long this video is getting, but hopefully you found it helpful.